Okay, we were talking about Lewis dot structures of don't worry about that. Just sign it at this point. There's no credit for. Thank you. We were talking about Lewis dot structures, and in particular for Lewis dot structures of systems that underwent what we called resonance. Resonance was defined as occurring when there was a single bond adjacent to a double bond between the same atoms. And we were looking at ozone, and what we said basically was there are two different places you could put this double bond. And neither one of the Lewis dot structures, when you have done that by themselves, adequately describe the molecule, because the molecule has two equivalent oxygen-oxygen bonds. The distances are exactly the same. So it wouldn't be right to write one double bond and one single bond, because we'd expect those to have two different bond distances. So what we did was to invoke resonance, and the two resonance structures were viewed as being the parents of something we call the resonance hybrid, in which we took the two Lewis dot structures here and averaged them in one way to describe it. And what we got was there's a pair of electrons involved in a double bond, which can be here or it can be here. And so we spread out, we delocalize it across both of those bonds so that in the resonance hybrid, this is called the resonance hybrid here, this dotted line represents one pair of electrons spread out between two bonds. There's also a lone pair of electrons in that as well, but as far as the bond order goes, that doesn't have any big significance. So each bond then consists of a single bond, a localized electron pair bond, and a partial bond, which is part of a delocalized electron pair. And the consequences of that were that if you look at the single bond and the double bond and think about an average of them, this hybrid had something between a single bond and a double bond. Now, delocalization is a good thing because it stabilizes molecules by spreading out electron clouds and making the electron-electron repulsion less, okay? Reducing the electron-electron repulsions. So this is what we've done over here in this red circle-y thing, spreading out a pair of electrons across two bonds to make the whole system more stable. Now, if we want the bond order for ozone, the oxygen-oxygen bond order, we can look at just one of these resonance forms. And we see there are two linkages. This is one, and this is one. There are 1, 2, 3 pairs of electrons for two linkages. So 3 electron pair over 2 bonds. I'm going to put bonds in quotes here because I really mean linkages, oxygen-oxygen linkages, and that will give us 1.5 electron pair for each link, or each bond. And so that'll mean the bond order is equal to 1.5, something between a single bond and a double bond. And since these two are the same, it would make sense that they each contributed equally to the resonance hybrid. Do you have a question on resonance? The things you should know include when to expect resonance, and that is when there's a double bond and a single bond, or a multiple bond and a single bond, adjacent to one another involving the same atoms, and how to represent the resonance hybrid and figure out what its characteristics would be, including its bond order. Everybody comfortable with that? All right. The last part is thinking about the resonance hybrid in terms of its characteristics. In this case for ozone, they were two equal oxygen-oxygen bonds, and they each had a bond order of 1.5. That's what we were talking about. Okay, let's look at the carbonate ion. After 4 steps, the carbonate ion Lewis dot structure looks like this. There are 2 carbon-oxygen single bonds and 1 carbon-oxygen double bond. So we know from that carbonate ion will be involved in resonance, and the resonance will differ in where the double bond is. So I'll draw one of these for you. Two negative charges on the carbonate ion overall. So this one has the double bond between the carbon and the lower left-hand oxygen. This one is the carbon in the lower right. So I'll let you write the last one. You can figure out where that goes. Now notice if we look at either of these, there are 3 carbon-oxygen linkages. And there are 1, 2, 3, 4 pairs of electrons that are participating in those linkages. And therefore, the bond order would be 4 pairs of electrons divided by 3 linkages, and the bond order would be 4/3 or 1 1/3 or 1.333, something like that. Okay? And all of the carbon-oxygen bonds we would predict would be equal and equivalent. And in fact, they are. The molecule, or the ion in this case, has exactly equivalent carbon-oxygen bonds. I'm going to put over here a representation of the resonance hybrid. Okay, this is not a resonance form. This is a resonance hybrid. I'm not going to fill in all of the electrons. I'm just going to show that you have a pair of electrons in the pi bond over here, a multiple bond, and in the resonance hybrid, that's spread over 3 bonds, like that. So this is what the resonance hybrid would look like. All the carbon-oxygen bonds are equivalent to one another, and they all have a bond order of 4/3. Questions on that? Okay. Another one here is the nitrate ion. I want to go over that with you. If you go through the rules for writing down the Lewis dot structure for the nitrate ion, after the 4th step, we get something, before the 4th step, we get something that looks like this, where there's no octet for the nitrogen. So we have to make an octet for the nitrogen. That's the first order of business. We change 1 lone pair on an oxygen to a double bond. And so if I pick that pair of electrons right there, I make a double bond between the nitrogen and the top oxygen here. And then I can see from that I have a single nitrogen-oxygen bond and a double nitrogen-oxygen bond adjacent to one another. So I will have resonance forms. And those resonance forms differ in where the double bond is placed. Here they are, double bond up, double bond lower left, double bond lower right. And again, if we wanted to describe the hybrid, we could do it. We have 1 double bond spread over 3 nitrogen-oxygen bonds, and this is pretty much just like carbonate ion. Nitrate ion and carbonate ion are described very similarly. So we would write in the backbone here, and then we would put in the dotted line that indicates that 1 pair of electrons is spread over 3 bonds here. And so the bond order would again be 4/3, just like it was for carbon. Questions? Okay. Now, these have been pretty simple cases because all of the resonance forms look almost exactly the same. That is to say, the only difference is the position of the double bond here. That is not always true, so the next thing we need to do is to decide how to deal with the cases where it's not true. Because if we want to describe the resonance hybrid, we can't just assume that each one of these non-equivalent resonance forms contribute the same amount. We can't do it. So if we have some sort of symmetrical structure like ozone, there's no problem because the resonance forms were equally mixed and each contributed to the same amount to the resonance hybrid. When that isn't true, one resonance form will generally be the most important resonance form. It'll make the biggest contribution to the resonance hybrid. The resonance hybrid's characteristics will be most similar to that. Now, the first problem we face, the biggest problem we face, is deciding which is the most important, which is the least important, and so forth. We have a way to help us. We have a tool. It's called the formal charge. The formal charge is another bookkeeping method to give some indication of how the electrons in a molecule or an ion are distributed and how each atom fares with respect to how it was as an individual atom. The formal charge is determined by an equation, and you need to learn the equation. The formal charge, or simply Fc, is equal to the number of valence electrons that an atom has as an atom, minus the number of unshared valence electrons, meaning lone pair electrons in the molecule or the ion, minus 1/2 of the shared ones. So the lone pairs count 100% for the atom we're talking about. The shared pairs, or the bonding pairs, count half to each one of the atoms that are involved in the bond. Now, a couple of things that fall out of this. If you use this little equation and you use it correctly, you'll find out that the formal charges will sum up to the actual charge on the structure that we're talking about. If the structure is a molecule, then the formal charges will sum up to 0. If the structure is an ion, either a polyatomic cation or anion, the formal charges, if they're calculated correctly, will sum up to the ionic charge, +1, +2, -1, -2, so forth. So I need to show you the application of this, but draw a circle around this because you need to learn the equation for calculating the formal charge, because we're going to be doing it frequently. Number of valence electrons of the atom minus the lone pair electrons in the valence in the compound, minus 1/2 of the bonded electron pairs in the compound. Okay, now in ozone, we could calculate the formal charge on, let's say, structure 1 here, and we've put some labels on the oxygen atoms here. These are just stick-on labels. They don't have any significance. Oxygen atom A in structure 1 has a formal charge which is 0, meaning that it has the same number of electrons, according to the scheme, around it as it did as an oxygen atom. So nothing big has happened to this oxygen. It's pretty much like it was as an oxygen atom. So here's the atom to look at. And oxygen came to the dance with 6 electrons. And so the calculation is pretty straightforward. We start with 6 electrons. There are 4 electrons in a double bond to that oxygen, so we're going to subtract 4 unshared electrons. Oh, I'm sorry, said the wrong thing first. There are 4 lone pair electrons here, so we're going to subtract 4 unshared electrons. And there are 4 bonded electrons here in bonding pairs, and so we're going to subtract 1/2 of that 4 because this is shared between the 2 oxygens here. So it's 6 minus 4 minus 1/2 of 4, which is 2. 6 minus 6 is 0. So we put in parentheses above this oxygen atom a 0. Okay? That means that oxygen atom is energetically very in a favorable circumstance. So we'll remember that. And what we're going to do first is to learn how the calculation works, and then I'll show you what the numbers mean, because that's a critical thing. But we've got to get the numbers right first. Okay, if we do the other formal charges on structure 1 here, oxygen A, as we said, is 0. Oxygen B came with 6 electrons. It has 2 lone pairs, and it has 2, 4, 6 bonding electrons. So oxygen B is 6 as an atom, minus 2 electrons that are lone pair electrons, unshared, minus 1/2 of 2, 4, 6 that are shared here. That gives a plus 1. So if we look at this, we'll put a parentheses plus 1 here for that oxygen. Now, I want you to recognize right now that I said that the sum of the formal charges has to add up to the charge. If it's a molecule, it has to add up to 0. So we can, by inspection, show that this oxygen must be -1, right? -1 plus 1 is going to give us 0. Or we can go ahead and calculate it. It is 6 minus 2, 4, 6 minus 1/2 of 2. 1/2 of 2 is 1. So 6 minus 1 is -1. So we have a -1 right there. So calculating it or just by inspection. Yes?
How are you counting the electrons? Are you counting it within the lone pairs? Like, is it 3 lone pairs and then...
The unshared electrons are the lone pair electrons.
So you're counting
Each pair is 2 electrons.
2 electrons.
Okay.
So that's how you're counting.
Yeah, yeah. See, with this oxygen over here, there are 2 pairs, 2 lone pairs, so I counted 4 electrons.
4. Okay.
Was there another question here? Okay, calculating the formal charge, let's look at B. B has oxygen C here with a 0 formal charge. And in fact, here's a trick that will help you. Any oxygen with 2 bonds to it has a formal charge of 0. Any oxygen with 1 charge to it has a formal charge of -1. And if it has 3 bonds to it, and a lone pair has a formal charge of +1. Anyhow, here are the formal charges. This oxygen has 1 bond, so it's -1. And this oxygen has 3 bonds and a lone pair, so it's +1. And you can see just what we expected is true here. The formal charges are the same. They're just on different oxygens as we go across here. All the oxygens were equivalent when they came in, but the center oxygen has a formal charge in both of these, a +1, and the single-bonded oxygen has a formal charge of -1, as you can see here. Now, if you look at that and say, well, will these 2 contribute equally to the resonance hybrid? Your answer should be yes. It certainly looks like they would. There's no really significant difference between them. But that doesn't always happen. So what I've said at the bottom here is they have the same formal charges, so they contribute equally to the resonance hybrid. Okay. Now, once we know the formal charges, there are some rules about what the formal charges mean as regards the contribution of any resonance form to a resonance hybrid. The first one is by far the most important. The first rule of formal charges is that small formal charges, whether they be plus or minus, are preferable to large formal charges, and 0 is the best of all. A 0 formal charge is as good as it gets. Okay? Now, there are 2 other rules that are less significant overall, and we always take our main lead from rule number 1 here. The smaller the formal charges, the nearer to 0, the better. Okay? If we have systems that have the same set of formal charges, but they differ in where the positive and negative charges are, the next thing we say is the same formal charge signs, plus and plus or minus and minus, on adjacent atoms is not desirable, meaning that that resonance form won't contribute as much to the resonance hybrid. And the third one is within one, more negative formal charges should be on the more negative atom if other things are equal. Okay, now these things aren't going to mean anything to you until I do my job here and show you how they apply. So I'm going to use the cyanate ion, NCO-, which is a 16-electron ion. And I am going to write the Lewis dot structures for you. And there are 3 of them that have octets, which have octets, period. In other words, they meet the criterion of having octets. The first one, of course, has the carbon in the middle. They all should have carbon in the middle because that's the lowest electronegativity atom there. They all should have carbon in the middle. But the first one has a single bond to nitrogen and a triple bond to oxygen. And when you do the formal charges, a single bonded nitrogen works out to have a -2 formal charge. Not good. Not good at all. The carbon in the middle has 4 bonds. It has 0 formal charge. The oxygen has 3 bonds in a lone pair, so it has +1. And algebraically, -1, -2, and +1 adds up to the charge on the ion. So it looks like we've done this correctly. But it also doesn't look like this, this resonance form is an extremely important one as regards to the resonance hybrid. So let's look at B. B has double bonds. Carbon-oxygen double bond, carbon-nitrogen double bond. Let's look at the formal charges there. Double bonded oxygen, 0. 4 bonds to a carbon makes 0. There's no lone pairs or anything. 2 bonds to a nitrogen with 2 lone pairs, when you do the calculation, makes -1. So this one has 2 zeros and a -1. That's clearly better than A for rule 1. Everybody see that? The formal charges are smaller in B. Now C has a nitrogen-carbon triple bond and a carbon-oxygen single bond. And 3 bonds to a nitrogen with a lone pair gives 0 formal charge. 4 bonds to carbon gives 0. 1 bond to oxygen, as we mentioned a little while ago, is, if you have 3 lone pairs, is a formal charge of -1. So notice both of these have the same set of formal charges, a 0, and a -1. So they're equivalent as far as rule 1 goes. And they don't have any formal charges, plus or minus formal charges on adjacent atoms, so we skip 2, and we go down to 3, and we look for the one that has a formal charge on that's negative on a more electronegative atom, and oxygen is more electronegative than nitrogen, and so C looks to be the most important resonance form with regard to the resonance hybrid. So A is less important than B and C due to larger formal charges. B and C have the same magnitude of formal charges, so form C has a negative formal charge on oxygen, which is more electronegative than nitrogen. So we would say the relative contributions to the resonance hybrid are C greater than B, and both of them a lot greater than A. Okay? You can almost put B greater than, double greater. Okay, so what does that mean to us? Well, it means if you look at B and C, the most important contributions, and you ask, well, what will the bond length of the carbon-nitrogen bond in the resonance hybrid be? Well, it'll be something between the bond length you'd expect for a carbon-nitrogen triple bond, which will be the greatest contribution to it, and a carbon-nitrogen double bond. The bond order will be somewhere between a triple bond and a double bond, so the bond length will be somewhere between a double bond length, and a triple bond length. And if we do the same thing for the carbon-oxygen bond, it'll be somewhere between a single bond, carbon-oxygen, and a double bond, carbon-oxygen. So without doing very much, we developed a pretty sophisticated picture of this resonance hybrid, which represents the molecule, meaning the resonance hybrid, if we've done it correctly, should tell us about the real molecule, or ion in this case, the cyanate ion. So in the real cyanate ion, we would expect, we know something about the carbon-nitrogen bond order and bond distance, and something about the carbon-oxygen bond order and bond distance. So this is the power of formal charges and what they can do for you. You have a question about this? I'm going to be using them extensively, and I know you need some practice on working on them, but now is everybody comfortable with how you do it? Okay, good, good.
Oh, I have a question. How did you get the numbers -1, 0,
By using the formula that I gave you.
with O?
Number of valence electrons minus the number of share that we've just talking about. Okay. Okay. Let's do this exercise. What's the formal charge on the middle atom of dinitrogen monoxide? Okay, if you can do this one, you could probably do any one that we're likely to encounter. So N2O has how many valence electrons? 2 times 5 plus 6 is 16 electrons. And what will be the center atom? It's a trick. We did that the other day. Nitrogen has less electronegativity than oxygen, so one of the nitrogens is going to be the center atom, and one is going to be a terminal atom. So I'll put them here and here like this. We have 16 electrons. We're going to make 2 single bonds. We're going to subtract 4 electrons. That's 12 electrons left. We're going to start putting them as lone pairs, making octets. That's 6, 8, 10, 12. We've used up all the electrons at this point, and we don't have enough electrons around the center nitrogen. So you know what we do, right? We make a lone pair turn into part of a double bond here. And we do the same thing over on this side. Then what will we have? Then we'll have a description like this. 2 double bonds, and nitrogen in the middle with a, if we look at the charges that are involved here, oxygen is 0, the formal charge. Nitrogen is +1, 4 bonded nitrogens +1, no lone pairs. Then we have 2 bonded nitrogen would be -1. Okay? So as we look at this, answer to the question is looked like +1, but there's some other ways that we could write this. So we better write those down just so we can see, because if they're different, then we have to think about the resonance hybrid. So we can do this. We can put in this resonance form. This is a 16-electron resonance form. The center nitrogen has +1 here. This oxygen's 3 bonded, so it's 0. This oxygen has just 1 bond, so it's -1. So both of these have a +1 formal charge on the central atom. Which one of these is going to contribute more to the resonance hybrid? Between the two of them, they both have the same charges, so charge doesn't matter. None of them have the same charge on adjacent atoms, so we go down to electronegativity, number 3, and it looks like this one with a negative charge on oxygen will contribute a bit more to the resonance hybrid than this one. What else have we got here? There's one more that I can draw that does the octet, all octets. This one has a single bond between the nitrogens and a triple bond between the nitrogen and the oxygen. That makes this oxygen +1 formal charge. Makes the nitrogen in the middle +1, and this nitrogen on the end -2. Will that contribute very much to the resonance hybrid? No, it's a bummer. It won't make a significant contribution. So we would know that the resonance hybrid here would have nitrogen-nitrogen bond between a double and a triple bond, and nitrogen-oxygen between a single and a double. But the question really asked about the charge on the center atom, and it was +1 all the time. If it weren't, we would have to look at the resonance hybrid and get some idea from that. Questions on dinitrogen monoxide? Yes? Yes. Look at rule 1 first. She asked, we do the formal charges first, and the answer is yes. And then within that, if there's more than one possibility, then look at rule 2 and rule 3.
So what is the formal charge to answer the question?
The formal charge is the charge calculated by that same formula that we just talked about.
Is it all of that?
No, the formal charge is this, right there, and right here. It's given in parenthesis above the atom that is calculated for. Yes? If you're comparing formal charges, you're just looking at the numbers. If they all have the same set of numbers, the formal charges are the same. If they have a different set of numbers, then you look, how far from 0 is it? The farther from 0, overall, the worse it is. Other questions? Okay, thank you. Let's go ahead. Now, we have been talking like the octet rule was inviolate. But in fact, there are circumstances where we will have Lewis dot structures that have non-octet atoms. To give you an example, if you look in the periodic table, beryllium is in group 2A. So it starts off forming a compound with only 2 electrons. And it becomes virtually impossible for it to get an octet because it started with so few. The same thing is true with boron. So molecules that have just 2 or 3 electrons when they start, if they're the central atom, they're going to be electron deficient, and probably there won't be any way we can give them an octet. That doesn't mean that it can't exist, and I'll show you some examples where we have Lewis dot structures which are accurate. They're accurate as far as we can tell. So I'm going to show you BeCl2 here, and if we look at BeCl2, the beryllium only has 4 electrons around it, and the chlorines are characteristically going to have a single bond. If we try to make a double bond to a chlorine, things don't work well. The same thing is true with fluorine over here. So you might ask, why don't lone pairs from the halogen make double bonds here and double bonds over here to satisfy the octet rule? And the reasoning is, if you do that with BeCl2 and make beryllium-chlorine double bonds, look at the terrible formal charges you have. This suggests that this structure, although you could write it down, doesn't make a big contribution at all to the resonance hybrid. In other words, the actual molecule is better described with beryllium, chlorine, single bonds, and with an electron-deficient beryllium. Okay, so atoms from group 2A that form molecules, realize most of them are ionic, but beryllium forms molecules, probably will be non-octet with their central atom. The same thing is true with boron. We have only 6 electrons around the boron when we draw single bonds. So if you wanted to draw a double bond here, you certainly could, but notice that makes 2 formal charges, a +1 and a -1, and it violates rule 2, doesn't it? Because fluorine is the most electronegative element, and we just put a formal charge on it, +1. That would give it a migraine headache, I'm almost sure. It would not like that, and if I can personify fluorine, this would not be an important resonance form. So that's one type of exception to the octet rule when the central atom starts off with too few electrons. Questions on that? Okay? The other end of the chain, I got one more thing to say about this. Sometimes such compounds have the tendency to make up the empty space around the center atom by forming a bond with an atom that has a lone pair. Like BF3 forms a bond with ammonia, makes a nitrogen-boron bond here. Both electrons in that bond come from nitrogen. We call that a coordinate bond or sometimes an adduct bond. And so that's what makes a compound like this hang together. It gives boron an octet. So in that respect, we would expect some stability from that. There are also so-called odd electron molecules, meaning the number of electrons is an odd number. If we look at some of these, they typically behave as what we call free radicals, meaning that somewhere in the molecule there's an atom that has, instead of a lone pair, it has a single lone electron. Okay, there are a number of these things around. Nitrogen dioxide is one. Count the electrons. 5 plus 2 times 6 is 12. That's 17 electrons. If you do the Lewis dot structure for nitrogen dioxide, what you find is that you can make an octet for this oxygen, octet for that oxygen, but 7 electrons for the nitrogen. You don't put a double bond here. Why not? You don't put 2 double bonds to the nitrogen because, say it louder, how many electrons is that? That's 9. That's not going to work. 9 is not acceptable. Don't ever write it down. If you take organic chemistry, it's like writing a structure with 5 bonds to carbon. There's no quicker way to get a big red mark on your paper that I know of. Don't do it. Remember, Gene Angel said, don't ever exceed the octet for carbon, nitrogen, oxygen, fluorine. Okay, sometimes these free radicals, if you cool them down, can form a bond from the 2 electrons that you have here. So if you cool down nitrogen dioxide low enough, nitrogen dioxide, incidentally, is a red-orange gas that plays a big role in air pollution. It's partly responsible for the fact that on a real bad air pollution day, you see kind of an orange tinge. And that's mostly due to this fellow. But if you cool it enough, it forms this bond and makes dinitrogen tetroxide here, and that has no color. So occasionally, free radicals will pair up to make octet OK structures. Now, the other thing is expanded valence shells. I have a couple minutes to talk about that with you. Molecules that have a central atom with Z is equal to 13 or more, in other words, greater than 12, can have what we call an expanded octet. Here's the periodic table. 13, well, you can't even see it here, but aluminum is element number 13. Z is equal to 13. So starting with aluminum, you can have an expanded octet, which means greater than 8 electrons. It usually happens when you have molecules or ions that are formed with highly electronegative substituents like oxygen and fluorine. Now, what's usually described here, but is still quite a matter of controversy, is that these elements with Z greater than 13, in order to accommodate more than 8 electrons, instead of just using their S and 3p electrons, orbitals, which can only hold 8 electrons, it uses its empty d orbitals. Some people believe that these orbitals are too high in energy to make a meaningful contribution. And then there are some other explanations that are sometimes used. For the purposes of this course, I am happy with using empty d orbitals. It's certainly a possibility. I can't rule it out. So here is an example. Sulfur is Z is equal to 16. The most stable compound that sulfur forms is this hexafluoride right here. This is a gas that's so stable, they use it in high voltage transformers to keep the transformers from arcing. It is so very stable, and it has sulfur with, count them, 2, 4, 6, 8, 10, 12 electrons. Okay? And that can only happen if d orbitals are participating, in our view here, to accommodate the electrons beyond 8. Here's another one, phosphorus pentachloride. Look at this, 5 bonds, so 10 electrons around the phosphorus. Again, this can happen because fluorine and chlorine are pretty electronegative elements, and the phosphorus has a high enough Z value to have empty d orbitals. I'll start there next time. Thank you very much for your attention, ladies and gentlemen. Yes. 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 Phosphorus starts with 5.
Yeah, but shouldn't we have like one electron here? So the number of them?
Phosphorus has an odd number, but you count all the electrons in the molecule, then it won't be odd. Try it. Hang on, 1 second. Because that would give you 4, and 4, and 1 is 9 electrons. Nitrogen can never have 9 electrons. It can never have more than 9. Okay? Okay, if you try to form a double bond with 1 electron right here, if you take 1 electron away from the oxygen, then the oxygen ends up with 9 electrons.
Oh, okay. Oh, yeah.
Okay? It's bad either way. Hi. Here. Yeah, just sign it. Can I help you? I am. I have office hours.
Let me see if I can get this out.
You want to come by?
I had thought to put up there that for this equation, number of valence electrons minus number of unshared atoms minus number of unshared minus number of shared.
There's a factor of half.
So is that what this makes this positive?
Yeah. For some reason, the parentheses here and the minus outside like that.
Oh, right.
Yeah.
I was just wondering. Oh, I just wanted to focus on the distribution of those. I should have put it.